Hello everyone, it's Caller from 19. It's day 22 in my challenge day, and today what I'm going to do is to finish the week 2 of this course and do some quiz and programming assignment and so on. Okay, let's start.
During the history of deep learning, many researchers, including some very well-known researchers, sometimes propose optimization algorithms and show they work well in a few problems. But those optimization algorithms subsequently were shown not to really generalize that well to the wide range of neural networks you might want to train. So over time, I think the deep learning community actually developed some amount of skepticism about new optimization algorithms. And a lot of people felt that gradient descent with momentum really works well. It was difficult to propose things that work much better. So RMS prop and the Adam optimization algorithm, which we'll talk about in this video, is one of those rare algorithms that has really stood up and has been shown to work well across a wide range of deep learning architectures. So this is one of the algorithms that I wouldn't hesitate to recommend you try because many people have tried it and seen it work well on many problems. And the Adam optimization algorithm is basically taking momentum and RMS prop and putting them together. So let's see how that works. To implement Adam, you would initialize VDW equals 0, SDW equals 0, and similarly VDB, SDB equals 0. And then on iteration T, you would compute the derivatives, compute dw, db using current mini batch. So usually you do this with mini batch gradient descent. And then you do the momentum exponentially weighted average. So VDW equals beta, but now I'm going to call this beta 1 to distinguish it from the hyperparameter beta 2 we'll use for the RMS portion of this. So this is exactly what we had when we're implementing momentum, except that I've now called the hyperparameter beta 1 instead of beta. And similarly, you have VDB as follows. So 1 minus beta 1 times dB. And then you do the RMS prop like update as well. So now you have a different hyperparameter beta 2 plus 1 minus beta 2 dw squared. Again, the squaring there is element-wise squaring of your derivatives dw. And then SDB is equal to this plus 1 minus beta 2 times dB. So this is the momentum-like update with hyperparameter beta 1, and this is the RMS prop. like update with hyperparameter beta 2. In the typical implementation of Atom, you do implement bias correction. So you're going to have V corrected. Corrected means after bias correction. dw equals V dw divided by 1 minus beta 1 to the power of t if you've done t iterations. And similarly, V dB corrected equals V dB divided by 1 minus beta 1 to the power of t. And then similarly, you implement this bias correction on S as well. So that's S dW equals V d divided by 1 minus beta 1 corrected of hyperparameter beta 1. And this is the RMS prop like update with hyperparameter beta 2. In the typical implementation of Atom, you do implement bias correction. So you're going to have V corrected. Corrected means after bias correction. dw equals V dw divided by 1 minus beta 1 to the power of t if you've done t iterations. And similarly, V dB corrected equals V dB divided by 1 minus beta 1 to the power of t. And then similarly, you implement this bias correction on S as well. So that's S dW divided by 1 minus beta 2 to the t, and S dB corrected equals S dB divided by 1 minus beta 2 to the t. Finally, you perform the update. So W gets updated as W minus alpha times. So if we're just implementing momentum, you'd use V dW or maybe V dW corrected. But now we add in the RMS prop portion of this. So we're also going to divide by square root of S dW corrected plus epsilon. And similarly, B gets updated as a similar formula. V dB corrected divided by square root S corrected dB plus epsilon. And so this algorithm combines the effect of gradient descent with momentum together with gradient descent with RMS prop. And this is commonly used learning algorithm. that's proven to be very effective for many different neural networks of a very wide variety of architectures. So this algorithm has a number of hyperparameters. The learning rate hyperparameter alpha is still important and usually needs to be tuned. So you just have to try a range of values and see what works. A common choice, really the default choice for beta 1 is 0.9. So this is the moving average, weighted average of dw, right? This is the momentum light term. The hyperparameter for beta 2, the authors of the Adam paper, inventors the Adam algorithm, recommend 0.999. Again, this is computing the moving weighted average of dw squared as well as dp squared. And then epsilon, the choice of epsilon doesn't matter very much, but the authors of the Adam paper recommended 10 to the minus 8, but this parameter, you really don't need to set it, and it doesn't affect performance much at all. But when implementing Adam, what people usually do is just use the default values of beta 1 and beta 2, as well as epsilon. I don't think anyone ever really tunes epsilon. And then try a range of values of alpha to see what works best. You could also tune beta 1 and beta 2, but it's not done that often among the practitioners I know. So where epsilon, and then try a range of values. This parameter, the be tuned. So you just have to try a range of values and see what works. A common choice, really the default choice for beta 1 is 0.9. So this is the moving average, weighted average of dw, right? This is the momentum light term. The hyperparameter for beta 2, the authors of the Adam paper, inventors the Adam algorithm, recommend 0.999. Again, this is computing the moving weighted average of dw squared as well as dp squared. And then epsilon, the choice of epsilon doesn't matter very much, but the authors of the Adam paper recommended 10 to the minus 8, but this parameter, you really don't need to set it, and it doesn't affect performance much at all. But when implementing Adam, what people usually do is just use the default values of beta 1 and beta 2, as well as epsilon. I don't think anyone ever really tunes epsilon. And then try a range of values of alpha to see what works best. You could also tune beta 1 and beta 2, but it's not done that often among the practitioners I know. So where does the term Adam come from? Adam stands for adaptive moment estimation. So beta 1 is computing the mean of the derivatives. This is called the first moment, and beta 2 is used to compute exponentially weighted average of the squares, and that's called the second moment. So that gives rise to the name adaptive moment estimation, but everyone just calls it the Adam optimization algorithm. And by the way, one of my long-term friends and collaborators is called Adam Coates. As far as I know, this algorithm doesn't have anything to do with him, except for the fact that I think he uses it sometimes. But sometimes I get asked that question, so just in case you're wondering. So that's it for the Adam optimization algorithm. With it, I think you'll be able to train your neural networks much more quickly. But before we wrap up for this week, let's keep talking about hyperparameter tuning, as well as gain some more intuitions about what the optimization problem for neural networks looks like. In the next video, we'll talk about learning rate decay. One of the things that might help speed up your learning algorithm is to slowly reduce your learning rate over time. We call this learning rate decay. Let's see how you can implement this. Let's start with an example of why you might want to implement learning rate decay. Suppose you're implementing mini batch gradient descent with a reasonably small mini batch. Maybe your mini batch has just 64, 128 examples. Then as you iterate, your steps will be a little bit noisy and it will tend toward this minimum over here, but it won't exactly converge. But your algorithm might just end up wandering around um, and never really converge because you're using some fixed value for alpha and there's just some noise in your different mini batches. But if you were to slowly reduce your learning rate alpha, then during the initial phases, while your learning rate alpha is still large, you can still have relatively fast learning. But then as alpha gets smaller, your steps you take will be slower and smaller. And so you end up oscillating in a tighter region around this minimum rather than wandering far away. Your learning rate over time. We call this learning rate decay, doing around and never really converge because you're using some fixed value for alpha and there's just your learning rate alpha. But then as alpha gets smaller, your steps tighter region around this minimum rather than wandering far away even as training goes on and on. So the intuition behind oscillating in a tighter region around this minimum rather than wandering far away even as training goes on and on. So the intuition behind slowly reducing alpha is that maybe during the initial steps of learning, you could afford to take much bigger steps, but then as learning approaches convergence, then having a slower learning rate allows you to take smaller steps. So here's how you can implement learning rate decay. Recall that one epoch is one pass through the data, right? So if you have a training set as follows, maybe break it up into different mini batches. Then the first pass through the training set is called the first epoch, and then you the second pass is the second epoch, and so on. So one thing you could do is set your learning rate alpha to be equal to 1 over 1 plus a parameter which I'm going to call the decay rate times the epoch num. And this is going to be times some initial learning rate alpha 0. Note that the decay rate here becomes another hyperparameter which you might need to tune. So here's a concrete example. If you take several epochs, so several passes through your data, if alpha 0 is equal to 0.2 and the decay rate is equal to 1, then during your first epoch, alpha will be 1 over 1 plus 1 times alpha 0, so your learning rate will be 0.1. That's just evaluating this formula when the decay rate is equal to 1 and the epoch num is 1. On the second epoch, your learning rate decays to 0.67, on the third 0.5, on the fourth 0.4, and so on. And feel free to evaluate more of these values yourself and get a sense that, as a function of your epoch number, your learning rate gradually decreases, right? As this, according to this formula up on top. So if you wish to use learning rate decay, what you can do is try a variety of values of both hyperparameter alpha 0 as well as of this decay rate hyperparameter, and then try to find a value that works well. Other than this formula for learning rate decay, there are a few other ways that people use. For example, this is called exponential decay, where alpha is equal to some number less than 1, such as 0.95 times epoch num times alpha 0. So this will exponentially quickly decay your learning rate. Other formulas that people use are things like alpha equals some constant over epoch num square root times alpha 0, or some constant k, another hyperparameter, over the mini batch number t square rooted times alpha 0. And sometimes you also see people use a learning rate that decreases in discrete steps, where for some number of steps you have some learning rate, and then after a while you decrease it by 1/2, after a while by 1/2, after a while by 1/2. And so this is a discrete staircase. So far we've talked about some using some, formula to govern how alpha, the learning rate, changes over time. One other thing that people sometimes do is manual decay. And so if you're training just one model at a time, and if your model takes many hours or even many days to train, what some people will do is just watch your model as it's training over a large number of days, and then manually say, oh, it looks like the learning rate slowed down. I'm going to decrease alpha a little bit. Of course, this works, this manually controlling alpha, really tuning alpha by hand, hour by hour, day by day. This works only if you're training only a small number of models, but sometimes people do that as well. So now you have a few more options for how to control the learning rate alpha. Now, in case you're thinking, wow, this is a lot of hyperparameters, how do I select amongst all these different options? I would say don't worry about it for now. In next week, we'll talk more about how to systematically choose hyperparameters. For me, I would say that learning rate decay is usually lower down on the list of things I try. Setting alpha, just a fixed value of alpha, and getting that to be well tuned has a huge impact. Learning rate decay does help. Sometimes it can really help speed up training, but it is a little bit lower down my list when in terms of the things I would try. But next week, when we talk about hyperparameter tuning, you see more systematic ways to organize all of these hyperparameters and how to efficiently search amongst them. So that's it for learning rate decay. Finally, I also want to talk a little bit about local optima and saddle points in neural networks so you can have a little bit better intuition about the types of optimization problems your optimization algorithm is trying to solve when you're trying to train these neural networks. Let's go on to the next video to see that. In the early days of deep learning, people used to worry a lot about the optimization algorithm getting stuck in bad local optima. But as the theory of deep learning has advanced, our understanding of local optima is also changing. Let me show you how we now think about local optima and problems with the optimization problem in deep learning. So this was a picture people used to have in mind when they worried about local optima. Maybe you're trying to optimize some set of parameters, I'm going to call them W1 and W2, and the height of the surface. Surface is the cost function. So in this picture, it looks like there are a lot of local optima, in all those places, and it'd be easy for gradient descent or one of the other algorithms to get stuck on a local optimum rather than find its way to a global optimum. It turns out that if you're plotting a figure like this in 2 dimensions, then it's easy to create plots like this with a lot of different local optima. And these very low dimensional plots used to guide our intuition. But this intuition isn't actually correct. It turns out if you train a neural network, most points of zero gradients are not local optima, like points like this. Instead, most points of zero gradient in a cost function are actually saddle points. So that's a point with a zero gradient. Again, this is maybe W1, W2, and the height is the value of the cost function j. But informally, a function of very high dimensional space, if the gradient is zero, then in each direction it can either be a convex light function or a concave light function. And if you're in, say, a 20,000 dimensional space, then for it to be a local optima, all 20,000 directions need to look like this. And so the chance of that happening is maybe very small, maybe 2 to the minus 20,000. Instead, you're much more likely to get some directions where the curve bends up, like so, as well as some directions where the curve function is bending down, rather than have them all bend upwards. So that's why in very high dimensional spaces, you're actually much more likely to run into a saddle point like that shown on the right than the local optimum. Oh, and as for why this surface is called a saddle point, W1, W2, and the height is all those places, and it'd be easy for gradient descent or one of the other algorithms to get stuck on a local optimum rather than find its way to a global optimum. It turns out that if you're plotting a figure like this in 2 dimensions, then it's easy to create plots like this with a lot of different local optima. And these very low dimensional plots used to guide our intuition. But this intuition isn't actually correct. It turns out if you train a neural network, most points of zero gradients are not local optima, like points like this. Instead, most points of zero gradient in a cost function are actually saddle points. So that's a point with a zero gradient. Again, this is maybe W1, W2, and the um, height is the value of the cost function j. But informally, a function of very high dimensional space, if the gradient is zero, then in each direction it can either be a convex light function or a concave light function. And if you're in, say, a 20,000 dimensional space, then for it to be a local optima, all 20,000 directions need to look like this. And so the chance of that happening is maybe very small, maybe 2 to the minus 20,000. Instead, you're much more likely to get some directions where the curve bends up, like so, as well as some directions where the curve function is bending down, rather than have them all bend upwards. So that's why in very high dimensional spaces, you're actually much more likely to run into a saddle point like that shown on the right than the local optimum. Oh, and as for why this surface is called a saddle point, if you can picture maybe this is a sort of saddle you put on a horse, right? So maybe if this is a horse, I guess there's the head of a horse, there's the eye of a horse, you know, I guess, and right, well, not a great drawing of a horse, but you get the idea. Then you, the rider, would sit here in the saddle. So that's why this point here, where the derivative is zero, that point is called a saddle point. It's really the point on the saddle where you would sit, I guess, and that happens to have, derivative zero. And so one of the lessons we learn in history of deep learning is that a lot of our intuitions about low dimensional spaces, like what you can plot on the left, they really don't transfer to the very high dimensional spaces that our learning algorithms are operating over. Because if you have 20,000 parameters, then J is really a function over a 20,000 dimensional vector, and you're much more likely to see saddle points than local optimum. If local optima aren't a problem, then what is a problem? It turns out that plateaus can really slow down learning, and a plateau is a region where the derivative is close to zero for a long time. So if you're here, then gradient descent will move down the surface, and because the gradient is zero or near zero, and because it's a region where the derivative is close to zero for a long time. So if you're here, then gradient descent will move down the surface. And because the gradient is zero or near zero, the surface is quite flat. You can actually take a very long time, to slowly find your way to maybe this point on the plateau. And then because of a random perturbation to the left or right, maybe then finally, I'm going to switch pen colors for clarity. Your algorithm can then find its way off the plateau. But I had to take this very long, slow path before it's found its way here and then could get off this plateau. So the takeaways from this video are, first, you're actually pretty unlikely before it's found its way here and then could get off this plateau. So the takeaways from this video are, first, you're actually pretty unlikely to get stuck in bad local optima so long as you're training a reasonably large neural network. So you have a lot of parameters and the cost function j is defined over a relatively high dimensional space. But second, that plateaus are a problem and they can actually make learning pretty slow. And this is where algorithms like momentum or RMS-prop or Adam can really help your learning algorithm as well. And these are scenarios where more sophisticated optimization algorithms, such as Adam, can actually speed up the rate at which you could move down the plateau and then get off the plateau. So because neural networks are solving optimization problems over such high dimensional spaces, to be honest, I don't think anyone has great intuitions about what these spaces really look like, and our understanding of them is still evolving. But I hope this gives you some better intuition about the challenges that the optimization algorithms may face. So that, congratulations on coming to the end of this week's content. Please take a look at this week's quiz as well as the programming exercise. I hope you enjoy practicing some of these ideas with this week's programming exercise, and I look forward to seeing you at the start of next week's videos.
Is to increase the size of steps taken in which iteration is is to expect. This two between two is smaller than it all. It's faster than one. Before I going to end up today's recording, and let's recap first. So what I learned today is about atom optimization algorithm and learning rate decay, and the final one is the problem of local optima. The basic idea of atom optimization algorithm is to use advantages of RMS probe and momentum algorithm. So as we remember that we use exponentially weighted average concept in the gradient descent to keep the momentum of the direction of gradient descent. So in our ADAM optimization algorithm, we utilize the momentum algorithm first to update VDW and VDB. And then, as we already did in the RMS probe, to calculate new notification, which is SDW and SDB, we also use that in the ADAM optimization algorithm. And in the implementation, we also use bias correction for ADAM optimization algorithm. And in the RMS probe, we divided the actual DW and DB over by uh, the square root of SDW and SDB. But in this case, we divide the VDW and VDB, which is exponentially weighted average about the gradient descent, and we divide it by the square root of DSDW and SB, and the both parameter, both variables are is the bias corrected variables. And in this algorithm, we have some bunch of hyperparameters, and the alpha is most important to that we need to tune. And the beta 1 and beta 2 and epsilon is we can use default value for those hyperparameters. And the next thing that I learned is about learning rate decay. The motivation for this As you can see in this image, if we don't have a learning rate decay, it always keep the fixed value of learning rate. So when we reaches the global minimum, it always keep the same learning rate like previous. So we're around when they're around the relatively higher region of the global optimum. But if we decay the learning rate gradually while we are learning the process, we can the green path, our gradient descent path can leave around more tighter region in around the global optimal. So this is the basic idea. And to implement this, we use as a running rate 1/1 plus decay rate product element-wise product and epoch number. We multiply by it initial alpha value. And there's other formulas that we can use. And the last thing is the problem of local optima. And this is about, and we traditionally, zero value of gradient descent in the learning process is considered as local optima or global optima in the low dimensional cost function. For example, if we think of the height of this axis as cost function value, and the horizontal axis, which is also gonna for each other, is hyperparameters, is parameter axis. In this three-dimensional plotted of gradient descent, we can think of this zero gradient descent as a local optimal, and here is the only global optimal. But it actually turns out that the most point of zero gradient descent in the higher dimension is a set of points like this. Depending on the view direction of we see these points, it can be seen like the global extreme or global maximum or global minimum, depending on the way or we view these points. So the actual problem is the plateaus is not the local optimal problem. So and this region is where the derivative is close to zero for a long time. Like this, the gradient distance is already quite small, so it will change so slowly. So maybe it takes too long to get off this plateau region. So, and luckily, the optimization algorithm like ADAM can improve the learning speed in this case. Okay, that's all for today's recording, and thanks for watching.